here we are in Lecture 2, talking about rate laws. Now, a rate law is a mathematical formula. It's an empirical formula. It describes the reaction rate, the relative reaction rate, I should say, as a function of reaction concentrations, or reaction pressures, or however you're measuring the amount of reactants you have present. I want to specify, to emphasize that it cannot be predicted from the balanced reaction. You have to determine it through experimentation, because the rate law is a reflection of the complex pathway involved in the reaction mechanism, the actual steps that the molecules undergo in order to get from reactants to products. And that can be very simple or it can be very complex. But this is the general form of a rate law. You know, it's just the rate is equal to some constant k multiplied by the concentration of A raised to some power times the concentration of B raised to a different power raised to a concentration C in yet another power, okay, and so on. Just however many reactants you have, they're all involved in that way. Now, rate, as I said, it's however you're measuring the quantities involved. So it could be molarity per second, atmospheres per second, moles per second, you know. K is called the rate constant. It's specific to that reaction and that temperature. The units change from reaction to reaction. The units for the rate constant are whatever is necessary to make the units of the rate, you know, molarity per second, or atmospheres per second, or moles per second, or what have you. A, B, and C will be any or all of the reactants. Not every rate law depends upon the presence of every reactant. There's various reasons for that. You know, one reactant could just be so slow that it is the only thing that really matters, and everything else is just waiting for that one to catch up. So the rate will depend only on one reactant and not on any of the others. Or it could depend on two of them, but not on a third. You know, it can be, like I said, fairly complicated. Now, M, N, P, this is the order of each reactant. It's the exponent. It can be a whole number, or it could be a fraction. Okay, so it could be a to the 1, a to the 1/2, a to the second, a to the 2.35. It could be anything. But these are not, I want to stress this, they are not based on the coefficients from the balanced reaction. So here is a random made-up example of a rate law for a reaction that's also made up. 3A plus 2B plus 4C goes to form D plus 3E. The rate law, here made up, just the rate is equal to 0.1138 molarity to the negative 1.5, second to the negative 1, times A to the 1/2, B squared. Those units for K, K itself has to be determined experimentally, just like the exponents. And the units are just what is necessary to get you to molarity per second for the reaction rate. So if A is measured in molarity and B is measured in, molarity per second, and B is measured in molarity per second, then the negative 1.5 and the negative 1 on those exponents would get you to molarity per second for the rate. Okay. And then we have the orders for A and B. A is 1/2. Okay. Orders don't have to be whole numbers. They usually are, but not always. And so this reaction, it is half order, 1/2 order with respect to A, and it is second order with respect to B. So overall, the order is 2.5 or 2.5. Okay, that's just, you add up all of the individual exponents to get the overall reaction order. And that is a handy shortcut for describing the reaction exponents. It helps us to understand, and as we'll see later, how the reactants behave with respect to one another, and how quickly they are used up, and how the reaction rate depends on those particular reactants. Now, I'm certain you have been chomping at the bit, eager to learn how to calculate a rate law. Well, there are two ways to do it. They're both relatively similar. The old school method is the differential rate law. The newer method is the integrated rate law. The old school method requires more experimental setups, but less calculation. The newer method requires fewer experimental setups and more calculation. So as computers have become more common and cheaper, the integrated rate law has also become more common. You guys don't have access to that sort of stuff, so in lab, you will be doing the differential rate law, the older method. Okay. So you measure the reaction rate for the differential rate law, You measure the reaction rate for each experimental setup, and then you compare the different reactions, the different setups, in order to determine how reaction rate depends on each reactant. For the integrated rate law, you let the experiment run over time, and instead of measuring reaction rate, you're just measuring concentrations. And then you examine how the concentration changes with time, and that will tell you what sort of reaction order it is. So let's go ahead and take a look at the differential rate law, or how you find rate laws using the differential method. So first we have the differential rate law. You have to set up multiple reactions, and you compare the initial rate, or just the rate overall if you expect it to be consistent, for each of the reactions to a certain baseline. Okay? So here we have 3 reactants, and that means we have 4 reactions. Okay, and so run 1, setup 1, the first one, it's 1 molar for each of our reactants and a rate of 0.5 molar per second. Then run 2, we've changed A, and it's running at a rate of 1 molar per second. And reaction 3, run 3, we have changed B, and it's running at a rate of 0.5. And reaction 4, we have changed C. And just by comparing each of these reactions, in a pairwise fashion, we can get the order of the reaction for each of our reactants. So first we compare run 2 to run 1. That's what I have over here on the left, 2 over 1. Just means run 2 over run 1. And then we have each of our reactants, A, B, and C. A is 2 over 1. That means, in run 2, it's 2 molar versus 1 molar in run 1. B is 1 over 1. C is 1 over 1. So, and the rate, of course, the new rate, the rate in run 2 is 1 molar per second. The rate in run 1 was 0.5 molars per second. Now, B and C didn't change, so all we're looking at is how does changing the concentration of A change the reaction rate. So we can get rid of B and C. We're not looking at them. And the concentration of A was doubled. So 2, the doubling, raised to the x power, and x being the order for A, is equal to 2. Okay, so you double the reaction, it gets raised to whatever power A gets raised to, and that caused a doubling of the reaction rate. So what we see is that x is equal to 1. 2 to the 1 equals 2. So this reaction is first order in A. So whatever the rate is, you just take A and multiply it. It's just to the first power. Okay, doesn't need to be multiplied by itself or anything. Now, next, we compare run 3 with run 1. Okay, and when we do that, we see 1 over 1, 2 over 1, 1 over 1. B has changed. A and C are the same. So we ignore A and C. And our reaction rate was 0.5 over 0.5. The reaction rate for run 1 is 0.5 molar per second. For run 3, it's 0.5 molar per second. So it has increased by a factor of 1. It's the same. So when we double the concentration of B, it gets raised to some power x, And this equals an increase in factor of 1 for the reaction rate. Okay. 2 to the 0 is 1, so the reaction order for B is 0. It gets raised to the 0th power, meaning that the amount of B present won't affect the reaction rate. I mean, if it's not present, there will be no reaction, but if it is present, it won't change the reaction rate. More B does not speed things up, whereas more A does speed things up. Double the amount of A, you double the reaction rate. And finally, we have 4 over 1. Run 4 compared to run 1. Okay? So 1 over 1, 1 over 1, 2 over 1. Okay, A and B are now both the same each time, and C has doubled. And the reaction rate went from 0.5 in run 1 to 2 molar per second in run 4. It's for a change of a factor of 4. So 2 over 1 is 2. Raise it to some power for C, and what you get is that run C is, or run 4 shows that C is second order, okay? Because 2 squared is 4. 2 to the second power is 4. So it's second order in C. So our overall rate law that we have determined experimentally here is that the rate for this reaction, the relative rate, I should specify, is equal to some constant K multiplied by A to the first power multiplied by C to the second power. And B just doesn't show up at all. Okay? B needs to be present in the reaction chamber, but it's not going to affect the rate of the reaction. Now, for those of you who are a little bit more hopeless at the maths, there is a way to get your calculator to find this stuff for you, to find the exponents for you. Okay? So A to the B equals C. Okay, that's pretty much what we've been doing. 2 to the x equals 2, 2 to the x equals 4, 2 to the x equals 0. You can do that no matter what the numbers are, okay, by taking advantage of logarithms. Okay, so just take a log of both sides here. I'm showing you the math so that we can just get to the eventual answer. Take the log of both sides. Log of A to the B equals log of C. Now, thanks to the magic of logs, log of A to the B is equal to B log of A. And that's going to still be equal to log of C. Then you just divide each side by log A. You get B equals log C over log A. Okay, so your exponent is equal to the logarithm of one number divided by the logarithm of the other. So going back into terms of what we were doing before, x, the exponent we were looking for, is equal to the logarithm of the ratio of the rates divided by the logarithm of the ratio of the concentrations. Okay. So, again, going back to our previous example, 2 over 1, 3 over 1, 4 over 1, x for each one. You have log 2 over log 2. That gave us the exponent for A was equal to 1. Log 1 over log 2, the exponent for B is equal to 0. And log 4 over log 2 is equal to 2. Okay, so it was C squared. And you don't even need to really understand logarithm math. Just plug those into your calculator. And so long as you have all the parentheses in the right spots, then you will get the correct answer. And this will work no matter what your exponent might be, no matter what your numbers are. You can always plug them in. So for this example, and a new example, if you have one of your reactants, the concentration goes from 1 molar to 2 molar. Your rate goes from 0.5 molar per second to 0.7 molar per second. That's going to get you some weird numbers, right? Well, you find the ratios. Okay, the ratio of concentrations is 2 over 1. It's just 2. The ratio of your rates is 0.7 over 0.5 is equal to 1.4. Okay, so we're looking for the exponent for A. So x is equal to the logarithm of the rates divided by the logarithm of the concentrations. So it's the logarithm of 1.4 divided by the logarithm of 2, which means that the exponent for A is 0.5. It's half order in A. Now, why would you get a rate like that? Well, it's you can get strange numbers just because these are multi-step processes. We won't really be getting into those too much, but what we do for those will happen in later lectures, because I'm going to go ahead and call it on this one.